In Module 1 of Chapter 2, we are interested to discuss constant motion of a particle. In our everyday life, we face some situations where we find that an object cannot move freely. Rather, its motion is restricted by some conditions. During its motion, it is compelled to satisfy some conditions expressed either by equations or in equations. Such type of motion is known as constant motion. In this module, we shall discuss what is constant. Next, classification of constant will be discussed. Constant forces are also to be discussed. Dynamical system and its classification are to be addressed. Generalized coordinates and its necessity will also to be discussed. Degrees of freedom will be discussed in this module also. Now, what is constant? Any restriction imposed on the motion of a body is known as constant. For an example, consider the motion of a rigid body. A rigid body is defined as a system of particles in which the distance between any two particles remains constant at any time. That is, mod Ri vector minus Rj vector equal to Cij. Cij being constant, Ri vector and Rj vector being the position vectors of two particles. I and j are distinct integers run over all the particles of the system. Now, we are interested to discuss the classification of constants. Constants can be classified as follows. First one is Rheonomic constant. If the constant relation depends explicitly on time, then it is called moving or Rheonomic. General form of Rheonomic constant is f function of r vector, comma r vector dot, comma t equal to 0. Or this expression can be considered as inequation also. That is, f is a function of r vector, comma r vector dot, comma t greater or equal to 0, where r vector and r vector dot denote respectively the position and velocity vectors at time t. For an example, consider a deformable body. A deformable body is one whose shape can be changed easily. The motion of such a body is governed by the equation mod Ri vector minus Rj vector equal to function of t. Ri vector comma Rj vector, where I not equal to j and I comma j vary from 1 to n, being the position vectors of ith and jth particles respectively at time t, and f function of t is a function. This constraint relation is of the form f function of r vector comma t equal to 0. It is Rheonomic constant. Now, Scleronomic constant. If the constant is independent of time, it is known as Scleronomic or static. The general form of Scleronomic constant is f function of r vector comma r vector dot equal to 0, or f function of r vector comma r vector dot greater or equal to 0. Here r vector dot is the velocity. As an example, we consider a simple pendulum. For a simple pendulum with fixed string length, position vector of the bob r vector with respect to the fixed fulcrum at any time t must satisfy the constraint relation mod r vector square equal to L square, L being the constant length of the string of the pendulum. This relation is of the form f function of r equal to 0. It is independent of time, so Scleronomic. Now, the holonomic constant. If the constant relation is independent of velocity r dot or can be made independent of velocity, then such constant is called holonomic or geometric. If sum of the coordinates can be eliminated for a constant expressed as a relation between the coordinates and time only, then the constants are known as holonomic. Basically, holonomic constants are integrable algebraic relations among the coordinates. General form of holonomic constant is f function of r vector comma t equal to 0 or f r vector comma t greater or equal to 0, where r vector and r vector dot are respectively the position and velocity vector at time t. As an example, consider the rigid body. The distance between any two points Ri and Rj remains unchanged, that is Ri minus Rj square equal to Cij square. This is an example of holonomic constant. Non-holonomic constant. Non-holonomic constants are those which are not holonomic. General form of non-holonomic constant is given by f function of r vector comma r vector dot comma t equal to 0 or f function of r vector comma r vector dot comma t greater or equal to 0, where r vector and r vector dot are respectively the position and velocity vector at time t. Non-holonomic constants are of three types. Constant relations which are non-integrable are of non-holonomic type. These are constants which cannot be fully defined until the full solution of the equation of motion is known. Next one is constant relations expressed by inequalities. These are also non-holonomic constant. For an example, particles compelled to stay inside a box. Third one is problems under frictional forces. These give rise to another type of non-holonomic constants. Consider the example of movement of gas molecules in a spherical container of radius capital R. Gas molecules are constrained by the walls of the spherical container to move only within the container. If Ri vector be the position vector of the ith particle of the gas molecule, then the constant relation is given by xi square plus yi square plus zi square less or equal to capital R square. Origin is at the center of the sphere. Here the constant is non-holonomic as the constant relation is expressed as an inequality. Let us discuss about two types of constant. One is bilateral constant and another is unilateral constant. First of all, consider the bilateral constant. In case of bilateral constant, at every point on the surface, both the forward as well as backward motions are possible. General form of such constant is given by f function of r vector dot t equal to 0. This indicates that this constant is bilateral. In case of bilateral constant, we have mentioned that forward and backward motions are possible. So, we have the relation with greater or equal to as well as less or equal to sign, which finally gives equality sign. On the other hand, in case of unilateral constant, forward motion is not possible at a particular point on the constrained surface. As a result, only the backward motion is possible. So, general form of such type of constraint is given by small f function of r vector dot comma t greater or equal to 0. R gives the positional vector, r vector dot is the velocity, t is the time. Now, constant forces. The forces associated with these restrictions are called forces of constraints or constant forces. The basic properties of the constant forces are as follows. They are very strong, so it is difficult for the body under consideration to deviate slightly from the prescribed path or surface. The prescribed path or surface is the constant and the equation of the path or surface is the constant relation. Next, the main effect of the constant forces is to satisfy the constant relations. Next, constant forces are elastic in nature and appear at the point of contact of the surface. If in a dynamical system there are some constants, then all the coordinates are not independent, as the coordinates are connected by the constant relations. So, one cannot vary the coordinates arbitrarily. Moreover, the forces which are responsible for the restrictions are unknown to us. This creates some problems to solve the equations of motion, as the total force is unknown to us. For this, we have to overcome this type of situation. Now, a system of moving particles form a dynamical system. The set of positions of all the particles is called the configuration of the dynamical system. Cartesian coordinates are just fine for describing particles that can move unconstant throughout space. But when the motion is constant in some way, another choice of coordinates may be preferable. Thus, generalized coordinates help us to overcome such type of problem. Suppose a particle is constant to move in a circle in the xy plane. Then the constants are given by x square function of t plus y square function of t equal to capital R square, z function of t equal to 0, solution of which gives yt equal to plus minus root over capital R square minus x square function of t. There is an ambiguity in sign. This ambiguity can be removed as follows. If we use polar coordinates x equal to r cos phi, y equal to r sin phi, the constant simply becomes small r equal to capital R. You can note that the unambiguity just vanishes. So, in such case, it is better to use phi as the coordinate and phi dot as the velocity. Generalized coordinates. The independent coordinates required to specify or describe completely the configuration of a dynamical system at any given time are called generalized coordinates. A set of quantities q1, q2 up to qn which define the position of a dynamical system can be treated as generalized coordinates of that system, and q1 dot, q2 dot up to qn dot are known as generalized velocities. Any set of parameters which gives the unambiguous representation of the configuration of a dynamical system can serve the purpose of generalized coordinates. So, one can use angles, axes, moments or any set of parameters as the generalized coordinates. Proper choice of generalized coordinates is not an easy task. It depends on skill and practice. Right choice of generalized coordinates make the problem look easy, while the wrong choice of the generalized coordinates make the problem difficult to handle. Some examples of generalized coordinates are as follows. For a simple pendulum of length L, the corresponding generalized coordinate is the angular displacement theta, which is measured from the vertical. For a particle on the surface of a sphere, the corresponding generalized coordinates are theta and phi being the spherical polar coordinates. Let us consider a rod lying on a plane surface. In this case, the generalized coordinates are x, y and theta, where x, y are the coordinates of one end of the rod, while theta is the angle between the x-axis and the rod. Let us consider a lamina lying in a plane. For this case, the generalized coordinates are x, y and theta. Here, x, y are the coordinates of the centroid, while theta is the angle made by a line fixed in that plane. Now I come to classification of dynamical system. A dynamical system is said to be holonomic if, without violating the constant relation, it is possible to give arbitrary and independent variations to the generalized coordinates. Otherwise, it is known as non-holonomic dynamical system. More specifically, a system is said to be holonomic if it contains only the holonomic constants. On the other hand, if there is any non-holonomic constant, then the system is called non-holonomic. For example, let two particles of masses m1 and m2 connected by a string of length L be moving in space. If r1 vector and r2 vector are the position vectors of masses at time t, then clearly we have mod r2 minus r1 less or equal to L, which gives L square minus r2 vector minus r1 vector whole square greater or equal to 0. In this case, the system is a holonomic system with unilateral constant. Here two masses m1 and m2 are connected by a string L. The position vector of m1 mass is r1 vector measured from the origin O, while m2 mass having the position vector r2 vector. Next, consider the example of motion of a vertical wheel of radius a rolling on a perfectly rough horizontal plane specified by the coordinate axes Ox and Y. From figure 2.2, it is found the description of the physical problem. The contact point P traces out some curve C on the xy plane. If theta be the angle of rotation of the wheel, then the contact point P has travelled a distance s measured from the point P0 along the curve, then s is given by s equal to a into theta. We assume that the wheel rolls without sliding. Therefore, delta s equal to a into delta theta. If the coordinates of P are given by x and y, and if the tangent at P makes an angle psi with the x-axis, then delta x equals to cos psi into delta s equal to a cos psi into delta theta, whereas delta y is given by delta y equal to sin psi into delta s equals to a into sin psi into delta theta. The coordinates x, y, theta, psi form a non-holonomic system. The minimum number of generalized coordinates required to describe the configuration of a system or to specify the exact location of an object of that system is called the degrees of freedom. It is an important characteristic of any mechanical system. In other words, the minimum number of independent parameters required to describe the configuration of the dynamical system at any time is called the degrees of freedom. Consider an example. If a point mass is considered to move in a plane 2 dimension, the number of spatial coordinates necessary to describe its motion is 2. So, the degrees of freedom in this case is also 2. Consider a particle moving on a surface x square plus y square plus z square equal to a square. In this case, the degrees of freedom is 2, though the degrees of freedom in 3-dimensional Cartesian coordinate system is 3. If the particle is inside the sphere, that is, the equation satisfies such relation x square plus y square plus z square minus a square less than 0, then the degrees of freedom is 3. In this module, we have discussed the constant motion and the related matters. By a constant, we mean the restriction on the motion of a system of particles. The constants are expressed by some conditions written in the form of equations or inequations. The degrees of freedom and classification of dynamical system are also discussed in this module.